15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on the Space Nuts podcast. This is where we sit and chew the fat on all things astronomical. Well, not all of them, it'd take too long. But we do a few topics per week. And with me, as always, is astronomer at large, Fred Watson. Hi, Fred.
Hi, Andrew. How are you doing?
I am quite well, and you?
All the better for not attempting an Australian accent, yes.
Yeah, yes, we'll leave that in last week's episode. Today we've got some really fascinating stuff to talk about. The first topic is simply a question. What is life? This stems from an article asking that very question. And, we talked last week about aliens being able to pick up our radio signals thanks to a question. Well, now the question is, what is life and how do you define it? Well, that is a great question to try and mull over. There's been a new partnership deal between ESO and the world's largest gamma ray observatory. We'll talk about that. And as always, when we talk about the Big Bang and the expansion of the universe, people ask questions about the Big Bang and the expansion of the universe, and we've got one, but it's a ripper. So we'll focus on that thanks to Dayton Boyd a little later on. So, Fred, in the words of the great George Harrison, what is life?
It's something that makes my guitar gently weep, I guess.
While you're doing a bit of chewing on a Savoy truffle.
Yeah.
But it is an interesting question because we've talked many times about the search for extraterrestrials and signals from outer space. The WOW signal, we still don't know what that was. And we just assume it will be biological life, or we want to be on a level playing field. So we hope that any life we find, if ever, is basically as intelligent and as capable as us, or maybe not quite as. But where do you draw the line between what is life and what isn't, or how do you define it anyway?
Exactly. And, this is a question that people have wrestled with for a long time. And I guess the context is exactly as you've said. What are we actually looking for when we look out there? Are we looking for carbon-based life forms like ourselves? Are we looking for water-based life forms like ourselves? All of these things have alternatives. We, for example, think that there might be microbes living in the ethane and methane lakes of Titan, which are not based on water, but have their working fluid as these hydrocarbons. We don't know. So the idea of defining life has gone back a long, long way. One definition I remember hearing quite some years ago was that a living organism is a self-sustaining, self-replicating entity that is capable of Darwinian evolution. Which actually rules out me for a start. I don't think I can do any of those things. But that's a very, in a sense, a very blinkered definition, because that looks at what life is like on Earth and says, okay, this is what life does on Earth. Self-replicating, self-sustaining, capable of Darwinian evolution. But it may well be that there are some machines that could do that.
Well, I was about to say that. And what if we found a planet one day that used to have biological life forms that became extinct, but their machines had enough intelligence to self-replicate and improve and,
yes, exactly.
and continued on?
They're usually called von Neumann machines, after that great, I think he was an engineer, von Neumann, who or maybe even a philosopher, who said, yeah, if you've got machines that can make replicas of themselves, then they should be able to simply colonize the universe, basically. So you've got machines everywhere. But what is a machine? I mean, we might be machines, Andrew. We could be the end product of von Neumann machines. You
can stretch this in all directions and come up with all sorts of interesting theories and debate even argument, I suppose. It's definitely not one to solve by the water cooler, because you'd probably get sacked for wasting so much time. But it's just it really opens. It is a gargantuan can of worms, really.
It is,
which is a life form too.
Apparently it is. Yeah, that's right. Into this mix has come words from one of the great thinkers in this area, Paul Davies. He spent a long time in Australia, actually, working in Adelaide. He started off as a physicist in the University of Newcastle in the UK, but he then switched disciplines to astrobiology, the quest for life, or try and understand more about life and how it might form. And he now actually works in Arizona at an institute in Phoenix, just to the north of Tucson. So Paul is one of these people who, when he writes, you think, my God, that's amazing stuff. Why didn't I think of that? And he's drawn some really interesting strands together that come from history in many ways, because and I guess it's the history that's in fact it's an anniversary of some work that was done 75 years ago. I think that's what's caused him to set all this down in writing. Is life something fundamentally different from non-life? Well, let me read what Paul writes. 100 years ago, let me just go back to the paragraph before. Living organisms, and I'm quoting Paul Davies here, living organisms are so extraordinary, so unlike other complex systems we know, that they seem to be made of some sort of magic matter. And for centuries, it was widely supposed that organisms were indeed infused with a unique essence or life force to animate them. But then he says, 100 years ago, these mystical musings gave way to a mechanical view of life, according to which organisms are just immensely complex machines, obeying the same basic laws of physics as non-living systems. And that's kind of where we are. You know, we expect, okay, there's chemistry out there in space. We know there are complex molecules all over the place. Can they be organized into entities that would have what we might call the spark of life, something that, you know, is actually a living organism? And the 75th anniversary I mentioned was because of a book, actually. It started off, I think, as a series of lectures given by a person who's well known as a theoretical physicist, Erwin Schrödinger. We've all heard of Schrödinger's cat, the one that, you know, put in a box with poison and things like that. And it's a quantum theory. The quantum question is the cat alive or dead? And until you look, you don't know.
Yeah.
But it turns out that quantum physics is like that. You don't know whether an electron is this way up or that way up. And in fact, we now know that they're both ways up at once until you look at it, like looking at the cat. So Schrödinger was very much a thinker in theoretical physics. He was a bit of a lad as well, actually. He's got a terrible reputation as a philanderer, a philandering physicist. There's two PHs in there. So what he did was he noted that life seems to disregard one of the fundamental physical laws, which is called the Second Law of Thermodynamics. And the Second Law of Thermodynamics says that basically, as time goes on, things get more disordered. And, you know, if you think about it, that's the way the universe has worked. You start off with a Big Bang, in which everything, there was this kind of uniform plasma. It was completely ordered because there was nothing different. It was all one plasma. And now look at it. It's a complete mess. We've got galaxies and stars and planets,
dust and ice,
space
and
nuts and all kinds
humans.
of rubbish. Completely disordered. But life works the other way. Life creates order. You take disorder and you create order. And that's what Schrödinger was querying, the fact that life seems to go in opposition to the second law of Thermodynamics. There's a long, I'd recommend people to actually seek out Paul Davis's article. It's on the Cosmos website here in Australia, because he works through all these issues about how thermodynamics and living organisms interplay with one another, but points out that physicists today have looked upon another ingredient in all this. It's not just the chemistry and the biochemistry that make a living organism. There is information in there as well, and information almost becomes like a fuel to feed living organisms. So he's saying that biologists these days, and I'm quoting here again, now regard living organisms as networks of information flow coupled to networks of chemical reactions. Just as evolution shapes the architecture of cells and bodies, so it sculpts the networks that support the swirling patterns of information that makes organisms tick. And he has this lovely analogue. Regarding life as an intimate amalgam of chemistry and information is akin to the complementary roles of hardware and software in computers. Just as we need hardware engineers to design circuits and chips, so we need software engineers to design programs. So the outcome of all this is maybe the ingredient that makes life is that information flow that can traverse the chemical foundations that these complex molecules put in. And then what he says is the challenge for astrobiologists is to work out the generic features of such networks of information in case extraterrestrial life uses a different molecular basis. In other words, he's saying there's no point looking for the molecules. Don't look for, complex organisms, complex molecules. What you've got to look for is what the information does to change those molecules. And that's a bit hard to see what it might be.
Yeah, and it just keeps the question rolling over and over and over. And
it certainly makes it more complicated, that's right.
And you can't really come through with a basic definition. And the one element we haven't introduced into this discussion, which I'm sure has crossed a few minds, is the question of the soul.
Yes,
and the religious angle, because a lot of people define life by those elements.
That's right. And, that could be almost a different way of putting the same thing, that maybe the soul is a pile of information. I must just, if I may, and thanks to Paul, I know Paul reasonably well, so I think he wouldn't be miffed at me quoting verbatim from his article. It's a very nice article, but he winds it up with what I think is a really nice sentence. If Schrödinger were alive today, he might be surprised to learn that the answer to his question, what is life, is not that living systems are made of the right stuff, but that they encode the right bits.
Yeah, nice. Good
Great
conclusion.
Stuff. Great stuff,
Yeah, all right. It's a question that will be probably bounced around and debated and argued and decided upon and then torn apart again for quite some time. So anyway, it was really interesting to talk about. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson, of course.
Okay, we checked all 4 systems and team with a go.
Space Nuts.
Now, Fred, we're going to look at a collaboration, a cooperation, a deal, a partnership, whatever you want to call it, between the European Southern Observatory and the world's largest gamma ray observatory. That's a new development, and I'm guessing that the people involved are getting as excited as these kinds of people can get.
Absolutely. I think it is pretty exciting, actually. This is a branch of astronomy that is relatively unknown to me, because I'm not terribly clever in stretching myself to the different wavelengths that astronomers can detect. So we tend to think of astronomy as just looking at the sky. And when we look at the sky, what we see is the effect of visible light. And using big telescopes to detect that visible light is called optical astronomy. But of course, we know that the universe emits radio signals as well, and there's radio astronomy. And we know that it emits X-rays and things of that sort, which leads to the astronomies that need to be done above the Earth's atmosphere. But the universe also emits radiation at the very highest energies, and they are what you call gamma rays. So gamma rays are like visible light, but absolutely supercharged. They're very high energy. It means if you think of them as waves, they're very short wavelength radiation. How do you detect gamma rays? There's a number of ways of doing it, but
I would suggest you use a gamma ray observatory.
Oh my God, what a great idea.
I think that's a good idea.
Thought of that. Yeah, it's better than using an optical observatory. Although, as it turns out, the two are almost the same thing. And that's because gamma rays are so energetic that when they come through the Earth's atmosphere, they basically create radiation, which is called Cherenkov radiation. It comes about because the gamma rays are moving through an atmosphere. They're coming in at the speed of light because that's the speed with which they travel. When they get in the Earth's atmosphere, though, the local speed of light is lower than what it is where they've just come from. And that's because any refractive medium, like glass or air, slows down the light as it goes through it. So
I didn't know that. I would have thought that the speed of light was a constant.
It's constant in a vacuum, but not as soon as you put any medium in there. So these gamma rays hit the Earth's atmosphere and find themselves in a medium where the speed of light is actually lower than what they're traveling at. And so they emit a shock wave. That's basically what it is. And this shock wave is visible light. It's a thing called Cherenkov radiation. It's really interesting stuff about which all I really know about it comes from third-year physics about 150 years ago. But what it means is if you've got gamma rays coming into the Earth's atmosphere, you can detect them by flashes of light, visible light. And so these are very, very faint. And so you need big telescopes to detect them. You also don't really need telescopes that have that exquisite perfection of the big telescopes of the world with the ability to image things in the most fine detail. You don't need to do that. All you want to look for is things that are flashing roughly in the direction that you're pointing the telescope in. And so it means you can build very big telescopes with what are called segmented mirrors, hexagonal components. And I've actually stood beside one of these telescopes with a mirror about 30 meters in diameter, which is colossal.
Yes.
And it's made up of these hexagons. That was called the Hess Telescope, the High Energy Stereoscopic System, I think it stands for. That's in Namibia. A very large telescope stands in the desert of Namibia where it hardly ever rains and basically looks at the sky, searching for these Cherenkov flashes from gamma rays. This is such an exciting branch of astronomy because the high energy processes that we can detect by that are all the exciting stuff that happens in black holes and neutron stars and exploding stars and all of the good stuff, as well as the Big Bang. And so we now have this proposal to build something called the CTA, the Cherenkov Telescope Array, which has two halves to it, one in the northern hemisphere, actually at a place called La Palma. And once again, there's a precursor there, which I used to be very familiar with, because I used to go and observe with the William Herschel telescope in La Palma. That's on the Canary Islands off the coast of Africa. So that's going to host the northern Cherenkov Telescope Array. But the southern array is going to be built in collaboration, as you said, with ESO, the European Southern Observatory, which is very much an optical observatory. And so a deal was signed just before Christmas, which involved ESO hosting the Cherenkov Telescope Array, southern part of it, very near the Cerro Paranal site of the the big telescopes, the 4 big ESO telescopes, the VLT, the Very Large Telescope. Why are we excited about this in Australia? Because Australia is a signatory to this. We are part of the deal with the CTA. So there was some excitement among the high energy community within the Australian astronomical community with this signing, which I think took place on the 19th of December, just before Christmas. It was the ESO's Director General who signed the deal with various other dignitaries, including an Australian representative. So this will be built at this site. We're talking about timescales of sort of, several years. It's not going to happen within the next few months, but it will be one of these projects that we expect will revolutionize our understanding of the universe in much the same way as that other high altitude array has, which is ALMA, the Atacama Large Millimeter Array, not very far from there, once again very high in the Andes, once again run by ESO, the European Southern Observatory.
Okay, I was going to ask you what they were hoping to achieve from all of this, but getting a better understanding of the universe is probably a good answer.
Yeah, actually it ties in as well with our growing ability to detect gravitational waves. The LIGO experiments, the Large Interferometric Gravitational Observatories, and other ones that are now coming on stream, these are now capable of detecting merging neutron stars, merging black holes, and things of that sort. And of course, these events, as well as shaking up the universe so you get gravitational waves, they also emit copious quantities of high energy radiation like gamma rays. And so the CTA, the Cherenkov Telescope Array, will almost certainly end up working closely in collaboration with organisations like LIGO to detect the gravitational waves. I think it's a very exciting future.
Indeed. Keep an eye on that, because there will certainly be more to report, and once they get this thing up and running, there'll be a heck of a lot more to learn, I imagine.
We hope so.
All right. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson.
0G, and I feel fine.
Space Nuts.
Lastly, Fred, a question from our audience, and we say a big hello to Dayton Boyd from Birmingham, Alabama. Never been there, but I'd like to. Sounds like a lovely place. Thanks for your question, Dayton. Appreciate it. And not surprisingly, Fred, because we talked about the expansion of the universe recently and the Big Bang, we got a question about the expansion of the universe and the Big Bang from Dayton. But it is one of those topics that just keeps on keeping on in terms of people's wanting to know. So let's get into it. Dayton says, greetings from Birmingham, Alabama. I've been listening since about episode 25 and haven't missed an episode since. Well, you've heard more than me. Thanks for the wonderful podcast. My question, I hear referenced often about the discovery of the universe is a surprise at the time, accelerating in its expansion. Why was this so surprising, and why are we sure that it will continue? For lack of a better example, a car is accelerating until it no longer accelerates. So could we still be in a period of initial acceleration? Will it slow down and cruise, or will it start contracting? I recall talk about the big crunch, but that seems to have fallen out of favour. Yes. Well, if I can just preempt where you're going to go with this, Fred, by saying the theory now, the modern theory is that the universe is expanding and is going to continue to expand at an accelerated rate. That's the modern thought, isn't it? There will be no big crunch.
Absolutely, that's right. Oh, you don't need me, Andrew. I'll just...
And it's fueling itself somehow as it expands.
Yeah, that's the trick. That is the trick. So a great question from Dayton. Thank you very much for that. And I suppose you're right in the sense that, if you looked at a snapshot of a car that was traveling along a road, there's a good chance you'd find that it was accelerating, that it was getting faster. A lot depends on what's happening, whether it's starting off or coming to an end. If it's getting to the end of its trip, you would find it decelerating. So that's the question that essentially faces astronomers. And the best way to look at this is actually to look at the history of it. So the observation that the universe is expanding is relatively easy to make, certainly by the standards of observing today. It's an easy thing to discover. It was discovered back in 1929 by Edwin Hubble, who used the Mount Wilson 100-inch telescope, the biggest telescope in the world at the time. He measured the speeds of galaxies and realized that the further away a galaxy was, the more rapidly it was moving away from us. And it turns out that if you look at that and do the calculations, what that means is that we are in the middle of something that's getting bigger, a universe that is expanding. The further away something is, the faster it's traveling away from us, and that says it's an expanding universe. We didn't know for many years whether that had always been the case. And it turns out that even though it's easy to measure that the universe is expanding, and we can tell how fast it's expanding now, there's something called the Hubble Constant, which is exactly what relates to that. But it's a lot trickier to determine whether it was always expanding at this speed and what it will do in the future. And that was the breakthrough. So exactly as Dayton said, in the 70s in particular, we were all convinced that because of the gravitational attraction, the self-gravity of everything in the universe, the galaxies, the stars, the planets, all of that stuff, because all of that has gravity, it was fully expected that that would slow down the expansion of the universe. And in fact, we used to talk about a deceleration parameter because we believed the universe was decelerating. We hadn't measured it, but that's what we believed was happening.
I grew up thinking we were all going to be crushed.
Because maybe one day, 40 or 50 billion years, when you'll definitely be an old man, so I wouldn't worry about that too much. But in 40
they will have perfected Zimmer frames by then.
Yeah. Well, my God, you'll need one at the age of 40 billion. I bet you don't look as good as you do now. 40 billion years down the track, we were expecting, that there would be this phenomenon that Dayton mentions called the Big Crunch, that it would be like a reversal of the Big Bang. In fact, Brian Schmidt used to call it the Gnab Gib.
Yes,
is the Big Bang backwards.
Yes,
because that's what it is. It's the reversal of the Big Bang. It's hard to say, Gnab Gib. But anyway, he was one of the two one of the two teams that in 1998 managed to measure whether the universe was accelerating or not, or decelerating or not, and got exactly the opposite answer what they expected. They expected it slowing down, but by looking at distant exploding stars, looking back to something like half the age of the present age of the universe, so you're looking back 7 billion years or so, it turns out that these things are further away than they should be. And that tells you that the expansion of the universe is accelerating. So you're faced with this fact. What do you try and do next? Well, you try and work out whether it's always been accelerating at the same rate, and that is still a work in progress. But all the evidence seems to be that it is, that this is a constant force that is basically causing the acceleration. It's something we call dark energy. And it turns out, if what we are measuring now turns out to be the final answer, and everybody thinks it will, it means that space itself has an energy which gets bigger as it expands. In other words, the energy is proportional to the volume of space. So as space gets bigger, the energy gets greater and it accelerates more. So this is telling you that the acceleration is not going to stop unless the laws of physics change. And this dark energy, whatever it is, this expansive, this kind of anti-gravity force, that's not going to go away by our current thinking. So the answer to will it slow down and cruise or will it start contracting, the best information we have at the moment is that it will continue to accelerate, and in fact it will accelerate at an ever increasing rate because there's more space and therefore there's more energy. And some people have suggested that far from the big crunch, what we'll get at the end is the big rip, where when we get to
breaks.
Where a stage, yes, where space-time itself at the quantum level just falls apart. Now, that's physics that we really don't have any handle on at the moment, but it's something that certainly some physicists believe could happen. So not a big crunch anymore, but a big rip. I'm not sure which is the worst, actually. I think both of those two alternatives are pretty grim, but thankfully neither of them are likely to be within our lifetimes.
Yes. And by then we'll be technologically advanced enough to build our own universe, so we won't need this one anymore.
Very likely, that's right.
Thank you, Dayton, for a fascinating question. Hope the answer was what you were hoping for, if that makes any sense at all. It did prompt a question in my mind, though, Fred, just to finish off. We, as the universe expands, we are expanding with it. We are moving through space and time. And so is everything else. And you and I have discussed before how there will be ultimately a time where everything's so far apart you can't see each other. Yeah. But at this point in time, do we know where we are in relation to the position of the Big Bang and the edge of the universe?
So the answer to that is no, and it's not a question that has an answer.
I thought the answer would be yes.
Ah, there you go.
So we don't know where we are.
No, well, I don't know where I am. I don't know about you. There's a stock answer to this question. Where did the Big Bang happen? And that is everywhere. And when you think about it, it does make sense, because the universe is everything. Neglecting for the moment the idea of multiverses, let's just think of our one universe. The universe is, by definition, everything we can observe or detect. And the universe, when the Big Bang happened, was all concentrated at a single point called a singularity. That single point has now expanded to be very, very big, and we don't know how big it is. It may not have an edge at all. We simply don't know. But because everything came from a single point, there is no center to it. We're all at the center because the center became the whole thing. So you can't, and our observations kind of, in many ways, support that. When you look out into the space, it really doesn't matter what direction you look in. You always see the same thing in terms of galaxies being distributed. So the universe is, to use the technical term, it's isotropic. It's the same in all directions. And that's exactly what you would get from a universe that expands from a singularity.
Okay. That wasn't really an answer, was it?
You've gone very quiet.
Yeah. I didn't think it would be that complicated.
Yeah, it just means there's no point in looking for a centre to the universe. Okay. Because in a sense, we are at it. Wherever you are, you're at the middle of the universe.
Yeah, well, that's, goes back to that theory about everything orbiting Earth.
Yes, that's right.
Which they used to believe.
Oh, they did, yes.
All right. Thanks again, Dayton, and we certainly do appreciate your questions. Keep them coming. We'll answer as many as we can, as often as we can. And Fred, thank you. As always, it's been a pleasure. It's always a pleasure, Andrew, and I look forward to the next time. I'll see you soon. See you next week, most likely. I hope so. That's Fred Watson, astronomer at large, who joins me every week here on Space Nuts. And thank you for listening, and we will talk to you again in a week or so. Space Nuts. You've been listening to the Space Nuts podcast. Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.